Hi all, I welcome you all to the next lecture today. Here Professor Ravi Kumar, School of Mechanical Engineering, Shastra deemed to be University. Today I am going to give you an overview of different kind of satellites, how satellites work, right? And what are the different application and classification of satellites. These are the general topics that we are going to cover today. In previous lecture, we have covered about introduction to orbital mechanics, where you have been introduced about different kind of orbits, and also we have given a clear idea about the Kepler's law. Kepler has basically given three laws of planetary motion. With the help of those, you can understand the planetary motions, and also in the current, Earth satellites, how actually they are working, their motion is happening in the orbit that can easily be understood with the help of Kepler's law. So today we will focus mainly on satellites. We will see different satellite orbits, how actually satellites are working, and then finally we will conclude the conclusion with the global positioning system GPS and its application. So let's start our discussion for today. So agenda for today discussion is introduction about the satellite. Then we'll go for how satellite works. Then we'll see satellite frequency and bandwidth, satellite classifications, and finally satellite orbits. And we'll end up with global positioning systems, right? And and their applications. So if we talk about the satellite, what is a satellite? A satellite is any object that orbits around another object, and the object about which the satellite orbits is called as primary. So satellites can be man-made or maybe naturally occurring, such as moons, comets, asteroids, planets, stars, and even galaxies. These can also be considered as satellites, natural satellites or artificial satellites. An example of natural satellite is Earth's moon. There are about 1,000 satellites in this space. Most of them are used for communication purpose. So, human-made devices are usually known as artificial satellites, and moon and asteroid galaxy. These are the example of naturally occurring satellites. So, we look at the satellite invention or discovery, how actually they started with. From science fiction, the first fictional depiction of artificial satellite launched into Earth, basically by Jules Verne in the novel called The Begum's Millions, 1879. So he has clearly written about the launching of satellite into the Earth orbit in that novels. So Jules Gabriel Verne, actually he was a French author and a pioneer of the science fiction genre. Verne was noted for writing about cosmic, atmospheric, and underwater travel before air travel and submarines were commonplace and before practical means of space travel had been devised. So at that time, he has written a lot of stories about cosmic, atmospheric, underwater travel, and some of those are now becoming reality. Alright, the first artificial satellite was Sputnik 1, launched by Soviet Union on October 4th, 1957, and that was the time. And after that, space race was started and followed by the USA. So how satellites usually work? You look at this pictorial presentation. So this is your uplink station, right? The first ground station. From there, signal will be sent. The signal will go and will be received by the satellite. The satellite will retransmit it, right, in footprint. So this complete, it will be the transmitted signal will be coming in this way, right, in both sides, and both of these signals will be received by two different locations, right, downlink stations, earth stations. They will receive it, right, and finally you can analyze data given by the satellite. So earth station sends a message message in gigahertz range to the satellite, right, that is called uplink, and then satellite receive and retransmit signals back, that is called downlink. So this will be coming like this. Retransmitted signals which are coming down towards the earth are known as downlink, and those will be received by the other station. Those are known as downlink earth stations, right? And this complete this process, that downlink and this receiving end, is known as the footprint, right? Basically it's known as footprint. So you look at the height, it is 22,300 miles uh, height at which satellite is situated from the equator, and this uplink station is sending the signal that is getting received by the satellite and retransmit back, and those are received by the other ground stations. Those are known as downlink, and the complete this pattern, right, this triangular pattern that you are getting here is known as footprint. Like that satellites do work. If we talk about the satellite frequency bands and antenna dishes, the size of satellite dishes antennas are related to the transmission frequency, how they are getting transmitted. So there is an inverse relationship between frequency and wavelength that we know already, right? So as wavelength increases, frequency will be decreasing. So larger antennas, particularly satellite dishes are necessary to gather the signal, because satellite is at very height, right? So from that height, if your frequency is coming, right, means frequency is coming, then wavelength means will be more, right? Length will be more, so frequency will be less. In order to get sufficient frequency, your antenna size should be bigger enough to capture the sufficient signals. So that's why larger antennas are needed to gather the signals, right, from the satellite. So if you look at the satellite frequency, most commonly used frequency bands are C band, particularly suitable for 4 to 8 gigahertz. Then Q band, a KU band, that is especially for 11 to 17 gigahertz. And recently, this last band came, that is KA band, that is basically suitable for 20 to 30 gigahertz. So earlier days we were using the C band, and for C band, the size of this antenna was bigger enough. So look at this. This is the size of this antenna. Now for DTH communication, particularly for DTS services and all, they are using KU band, and those operates in the range of 11 to 17 gigahertz. And particularly for radio navigation purpose, we use the Ka band or Ka band. So the satellite operate in different frequencies for the uplink and downlink. So we can summarize them like band and uplink gigahertz and downlink gigahertz. So C band, basically signals used to be sent by the ground station at the frequency between 3.7 to 4.2 gigahertz, and when they are retransmitting from the satellite, right, they will be coming by modulating at 5.9 to 6.4 gigahertz in C band frequency. If we are using the KU band, particularly we use the KU band for DTH services. So we do send the signal at 11.7 to 12.2 gigahertz, and they get modulated and retransmitted from the satellite at the frequency range of 14 to 14.5. And recently KA came, right. Ka band, that uplink is 17 to 21 gigahertz, and downlink is 27.5 to 30.5. And last one is LIS, right, which is basically for very low frequency range, very low compared to C. So it is coming between 1.6 to 1.625 gigahertz uplink, and downlink around 2.483 to 2.5 gigahertz. So, if we compare this, C-band frequency have been used in the first generation satellites and has become overcrowded because of the terrestrial microwave network employing these frequencies. So now we are not using it in current scenario. Earlier days we have used the C-band frequency, right? Especially this one. KU and KA, right? These two bands are becoming more popular, even though they are suffer from higher attenuation due to rain, but still, they are much popular compared to the C band. This is very low frequencies. This we are not using the satellites. So if we look at the classification of satellites, so particularly you can classify the satellite as per their purposes, right? for what purpose you are using the satellites. So if we look at the broad classifications of the satellite, traditionally we can say that meteorological satellites, particularly for weather forecasting, we do use these satellites. Radio and TV broadcasting satellites, right? Military satellites, particularly for taking the terrain information and all for that purpose. Special purpose satellites are there. Satellites for navigation and localization, that is called geostationary right positioning system, GPS system. That is for that purpose also we are using the satellites. So these are the traditionally traditional category of satellites. If we just focus on telecommunications, then global telephone connections, backbone of global networks, right? Connections for communication in remote places and global mobile communications. So if we look at the total number of satellites which are present in current scenario, if we say 1,000 satellites are there in the orbits, out of 1,000, 80% satellites are being used only for communication or telecommunication purposes. So if we look broadly on satellite orbits, four different types of satellite orbits have been identified depending on the shape and diameter of each orbit. So most favorable is basically GEO, that is called geostationary Earth orbit, that lies at an height of 36,000 kilometers above the Earth's surface, and this is the most stable orbit. In this orbit, if you are putting any planet, that planet means any satellite, and the satellite will make a complete orbit complete revolution in 24 hours. So the rotational speed of your satellite will be exactly equal to the speed of the earth. So if you want to get a proper position right on the earth, then very with single satellite you can capture certain area very accurately. So if you use just three satellites right in this GEO, that is called geostationary earth orbit, three satellites will be sufficient enough to cover entire surface area of the earth, and you can have accurate information about the positions and all. And especially all DTS communication used to be carried out by the satellites which are being placed in the geostationary earth orbit. All right, that's one thing. Then second category, or you can say just from the Earth, if you are going in the orbit, first orbit will come, that is called low Earth orbit. And low Earth orbit, also known to as, here whatever satellites you will be keeping, they will be in free fall towards the Earth. But as Earth speed is different than the speed of the lower Earth orbit, that's why they cannot enter into the Earth atmosphere because of the high magnetic field, right? But still, whatever planet is there, means, no, sorry, any satellite which is in low Earth orbit will keep on coming towards the Earth. So after every 3 or 4 months, you need to do the reboosting of the satellite. That means you have to change the altitude of the satellite, again regain the same orbit. Like our International Space Station, that actually that is lying in the low Earth orbit, and it is believed that the ISS is in the free fall situation, right? It is so every 3 months or 6 months when we are going for maintenance of ISS, we are reboosting it and we are changing the altitude. We are fixing the altitude right initially when it was placed. So over a 3 or 6 months, it will lose certain altitude, right? Because at low Earth orbit is very near to the Earth atmosphere, just above the Earth atmosphere. That orbit is known as low Earth orbit. So still, there will be a some portion of gravity there. It will not be exactly zero. So it will try to attract the objects toward the earth, but they will not enter into the earth because earth is rotating at different speed compared to the lower earth orbit. But there will be some loss of altitude, and that need to be corrected after every 3 to 6 months. So low Earth orbit basically lies at an altitude starting from 500 to 1500 kilometers above the Earth's surface. Then third category is MEO, that is called medium Earth orbit, or we can say ICO, intermediate circular orbit, that lies at 6,000 to 20,000 kilometers above the Earth's surface. Then finally, your highly elliptical orbit comes, that is beyond 20,000 kilometer, and highly elliptical orbit looks like completely elliptical of shape. So we usually do not want to put any of these satellites in the HEO. Usually we put either in LEO or we can put in GEO. GEO is the more stable because it's any satellite which is kept in GEO will be orbiting the Earth exactly in 24 hours. So the speed of the Earth and speed of the satellite will match. So exact precise location you can easily capture from satellite which is situated in GEO or geostationary Earth orbit. So this is the pictorial presentation of different satellite orbits. So this red one that you are seeing, this is known as geostationary Earth orbit, and this appears to be circular, right? Because it is at a very high altitude, around 35,768 kilometers, right? This first is that this is the Earth, and nearest the Earth, this orbit is known as low Earth orbit, right? So this is the example of different satellites, right? Global Star or Iridium. These are the some example of satellite which are here. Even ISS, International Space Station, is also lying in a low Earth orbit. Then after that, medium Earth orbit is here, right? It is here. This is medium Earth orbit, and this is the high Earth orbit or a highly elliptical Earth orbit. So we do not want to keep anything in this highly elliptical orbit. Either we can put low Earth orbit, middle Earth orbit, or lot of communication satellites are being placed in GEO, geosynchronous Earth orbit. So these are the different types of Earth orbits. So first, let we start from low Earth orbit. So the low Earth orbit, particularly, it is very nearer to the Earth surface. Just this is the Earth gravitational field. Just above that, this dot line in this orbit is known as low Earth orbit. So altitude is around 375 to 1000 miles. Revolution time, if you look at any satellite which is being placed in low Earth orbit, it will be revolving around the orbit in 90 minutes, or you can say 3 hours, because it's very closer. So advantages are reduced transmission delay, right? Eliminates need for bulky receiving equipment. So whatever signals are coming from low Earth orbit, for that receiver size will be smaller. So with the smaller size receiver, you can receive the signal and at better, frequency range. But what are the disadvantages? The disadvantage is small coverage area. So you need more number of satellites to be placed in order to cover larger area, right? So if you're putting just three satellites in here, you will be covering only very smaller, portion of the Earth. If you want to cover most of the Earth, right, at least two-third area of the Earth, you need minimum 24 to 30 satellites to be placed in low Earth orbit. So another way you can say it will increase the cost, right, of communication. So second disadvantage is shorter lifespan. It is just 5 to 8 years than the GEO. GEO is more stable atmosphere is there, 10 years. There your satellites may sustain 10 years, but here in low Earth orbit it will be just 5 to 8 years. So subdivision, then low Earth orbit is further subdivided into three categories: little, big, and mega super low Earth orbit. So little low Earth orbit, particularly in this frequency range, will be around 0.8 gigahertz range. So it is small and low cost, particularly. So this Earth orbit basically used for vehicle tracking, environmental monitoring, and a two-way data communication. Used for short and narrow band communications, particularly we use the little low Earth orbit. Next one is big low Earth orbit. Its frequency range is around 2 gigahertz, right? Can offer global services which can be subject to regulatory requirements. So you can see the video conferencing and all basically is being done by a satellite placed in big low Earth orbit. So used for technology devices such as high speed, high bandwidth data communications used as and video conferencing. They carry voice and high speed data services. The main uses are data communications and real time voice delivery to handheld devices. So all this basically lies in the big low Earth orbits. particularly. The next one is a middle Earth orbit. So if you look at the middle Earth orbit, this will be somewhere here. So altitude is around 8,000 to 20,000 kilometers, or in miles you can say between 5,600 and 9,500 miles. So these orbits are primarily reserved for communication satellites, right, that cover the north and south pole particularly. So all the communication satellites particularly being kept in the median earth orbit. So unlike the circular orbit which is here, right, like geosynchronous geostationary satellites, geostationary orbit looks like circular, right. MUR looks like elliptical, slightly elliptical, right, or oval shape orbit. So approximately a dozen of medium Earth orbit satellites are necessary to provide continuous global coverage of 24 hours. So this is another, and this can be say around a big disadvantage for middle Earth orbit. So more number of satellites are needed to provide a continuous coverage of 24 hours a day, right, particularly middle earth orbit. If you go further height, right, if you go in geostationary orbit, from there you will have a broader area coverage, right, easily you can cover broader area. But images if you are taking from geostationary orbit, you cannot get planar surface images. It will be looking like circular, earth will be looking like a circle, and over that you can visualize the cloud, completely cloud simulation. You can see how clouds are basically arranging. So all weather forecasting and communications are being done by the satellite placed in the geostationary orbits. But similarly, DTH, signals, DTH services are also operating by the satellites placed in the geostationary orbit, because the satellite placed in that orbit is basically rotating at the same speed as like the Earth. So Earth, any point on the Earth will be looking like a stationary. Or if you are at the Earth, if you are able to see the satellite in the geostationary orbit, that will be like stationary satellite. So if you select a particular region, and if you want to monitor that particular region, you can monitor it easily with perfect accuracy. So next one is geosynchronous Earth orbit. Orbit is synchronous with the Earth rotation, right? From the ground, the satellite appears as fixed. So this is the zone, right? Particularly, it's known as geostationary, right, or equal geosynchronous orbit. And any planet which is orbiting over this will be completing one complete revolution in 24 hours. So that means the rotation speed of the satellite in the geosynchronous Earth orbit is exactly the speed of the Earth. So from the Earth, if you are visualizing over the satellite will appears to be fixed. So altitude is around 23,000 miles, or you can say 36,000 kilometers from the mean sea level. So coverage to 40% of the planet per satellite. So one satellite can cover 40% of the planet. So if you put just three satellites will be sufficient enough to cover entire Earth surface. So geostationary satellites are commonly used for communication and weather observation. The typical service life expected for a geostationary satellites lies between 10 to 15 years. They complete one orbit every 24 hours. This causes satellite to appear stationary with respect to a point on the Earth, allowing one satellite to provide continual coverage of given area on the Earth's surface. Because geostationary satellites circle the Earth at the equator, so they are not able to provide coverage at the northmost or southernmost latitudes. So these are the two zones which are basically hidden from these satellites placed in the geostationary and geosynchronous orbit. Right? They are basically orbiting on the equator. So northernmost and southernmost latitudes cannot be visible by the satellites in the geosynchronous orbit. So if we look at the geosynchronous Earth orbits and weather, so this is the image basically taken from the satellite from the geosynchronous Earth orbit. So this produces the cloud and animation that you see in the TV. can take images approximately every minute. Every minute it can take the image, provide images of nearly one third of the Earth's surface every 23 minutes with 4 kilometer resolutions. So resolution will be very good, accurate, and it can give at least coverage of one third of the Earth's surface and can provide all the images in 23 minutes, every 23 minutes. So, United States maintains and operates its GEOs. The European community is served by its European Space Agency. Similarly, Japan's are having GMS satellite, which are basically placed in the geosynchronous orbit, and they are basically being used for weather forecasting. India has also launched uh, its own communication satellites in the geosynchronous orbit for weather forecasting. Now come to the global position system. As we know, GPS nowadays everybody is using for navigation, right? Particularly for navigation in the city or navigation anywhere on the place. So GPS is funded and controlled by the Department of Defense. So there are many countries or many thousands of civil users worldwide, but GPS was first designed for the use for the US military. Later on, they gave access to every country to use it. So GPS provides special satellite signals that can be processed in a GPS receiver, enabling the receiver to compute position and particularly velocity. So, four GPS satellite signals are needed in order to find out the three-dimensional position as well as the time offset in the receiver. So, minimum four satellites are needed to predict exact three-dimensional location of a particular object on the Earth. The Global Positioning System is a worldwide radio navigation system formed from constellation of 24 satellites and their ground stations. So they are constantly moving, making two complete orbits in less than 24 hours. So these satellites are traveling at a speed of nearly 7,000 miles an hour. So global position system is basically being monitored by 24 satellites, and they are kept in a different orbit. So in every orbit, approximately four satellites are basically traveling. So this is one of the example. At least four satellites are needed to find out exact location and velocity. So these are the four different satellites which will basically give signals to a single receiver here, and the single receiver will find out the dimension and means position and time via the receiver. And this is the constellation of 24 satellites, right? They are kept in this way, right? And so GPS nominal constellation are having 24 satellites in six different orbital planes. In every plane, either you can consider this or you can consider this. In every plane, you will find four satellites, right? They minimum requirement is four satellites. So four satellites will give signal to a single receiver, and the receiver will tell the exact location and velocity of the object. So if you look at the altitude where this this kind of 24 satellites have been placed, there are around 20 to 20,000 kilometer altitude and 55-degree inclination. So these all look at these different or elliptical rings are there, and every ring, whatever ring you will consider, you will find four satellites orbiting in that particular plane. So every plane is having four satellites. Total six orbital planes are there. This is an example of Navistar. So if we look at the broadly application of GPS, right? So as I said that the orbital period of GPS satellite is around 12 hours, right? So within a shorter period of time, they can give the exact location of any object which is moving through uh, on the earth. So whatever images that you will get from GPS will be plane images, so you can easily identify exact location and time. So let's suppose nowadays as technology has advanced, we can see like one fellow is in the building, and if he is running out of the building, we will see a point moving right from one direction to another direction. That point is nothing but a man. But exactly like in movies, they are showing that they are having GPS by which we can see the three-dimensional simulation. That is still not possible. That is not possible now because this GPS and all are kept at a very high altitude. The satellites which are sending the signal at a high altitude. So three-dimensional basically three-dimensional view is not possible exactly. Like buildings will be looking like three-dimensional kind of structure is very difficult, very difficult. But yeah, you can find out the correct location and you can get exact image of the particular object on the earth, or you can easily identify, like somebody is moving out from the building, he will be displayed like a point, that point is moving, so you can easily track exact location and the speed of the object, at what speed that object is moving from one point to the another point, that can easily find out. So some of the applications of GPS include aircraft navigation, marine navigation, driving, particularly surveying and farming. And these areas basically we are using the GPS, global position system. So this is the thing for today. So with this, I will close the today's discussion. Basically, so today we have covered basic introduction about the satellites, and you have been given an exposure how satellite used to work, and we have seen the classifications of satellite. Then we have seen what are the different bands that are being used in the satellite: C band, Ka band, Ku band, LIS band. And we have seen that out of these bands, Ku and Ka bands are becoming popular nowadays, but C band we were using in early satellites. Then finally we came to the GPS. We have seen the global positioning system. What is that, and how many satellites are minimum needed in order to predict the exact position and velocity. So as I said, total 4 satellites are needed in order to predict the position and velocity. But global position system is having 24 satellites. 6 satellites means 24 satellites arranged in these 6 different planes. Every plane is having 4 satellites, right? So like that, like that we are monitoring all the navigation around the world, and we have seen the various applications of GPS system. With this, I will close the today's discussion. In next class, again, I will come up with a lecture where we will discuss about other types of satellites and their working as well as application. So, thanks for your patience for listening to today's lecture. See you all in the next class. Have a nice day. Good day.